Okay, well, let's move on to 1909 when Lord Rutherford, and here he is, and his team, so Rutherford and his team, Geiger and Marsden, were, undertaking an experiment in Manchester, in the UK, to shoot alpha particles through a very, very thin gold foil. What are alpha particles? Well, alpha particles are fairly massive subatomic particles. We now know them to be 2 protons and 2 neutrons traveling at a very high speed. And where do they come from? Well, they come from the nucleus of an unstable atom. And in an unstable atom, you sometimes get radioactive decay, and an alpha particle is ejected to stabilize the radioactive atom, which literally changes its composition now that it's got rid of 2 protons and 2 neutrons. An alpha particle out of such a decay is traveling very fast indeed. We're talking about 10,000 kilometers per second. And so if you have a radioactive source here, then that's shooting alpha particles in all directions. We've got a little hole here, so we only have the alpha particles going in one direction here along this line, and they hit the gold foil. And what Rutherford's team observed was that about one in every 8,000 alpha particles were scattered through an angle that was greater than 90 degrees. Now, this was a very unexpected result, because going back to I've lost it. It's gone. Our ideas earlier. Here we are. Yeah, well, that's right. Remember we talked about the J.J. Thomson plum pudding and this model of the atom, where we've got this positive goo, and in there we've got then these electron plums just orbiting in various orbits inside the goo. So imagine that if you were firing an alpha particle going at 10,000 kilometers per second and into this sort of jelly-like substance. Well, it'd be like firing a bullet through a gun, wouldn't it? It'd be just sort of go straight through. Hardly any deflection would be expected, and that's what Rutherford and his team were expecting. They were really expecting only a few of these alpha particles to be deflected by very, very small amounts. What they found was that 1 in 8,000 were deflected through very, very large angles, which was very strange. So they had to come up with a new theory, a new model of the atom. And the model they came up with is one that looks very familiar to us now, because that's how we're taught. The classical model now is the nucleus is a very small part at the center of an atom, and most of the atom is empty space. The electrons orbit in shells. Yeah, so much for my stream, so much for my nice curves, but they orbit the nucleus in shells around the nucleus. The nucleus is positively charged because it contains protons. This is what they proposed. And the electrons are negatively charged and orbit, being pulled into the center through electrostatic attraction of a negative charge with positive charge. And that was the new theory. And hence the birth of this new theory. This is the birth of the nucleus. The nucleus idea. Give you an idea of the scale of this. If the nucleus scale, if an atom scale is about 10 to the minus 10 meters, that's 0.0000001 or thereabouts meters, very, very small. Then the scale of the nucleus of, in this case, gold nucleus, is 10 to the power of minus 15 meters. That is 100,000 times smaller than the atom size. 100,000 times smaller. So basically an atom is empty space with all of its mass concentrated at the center. Okay. So with this new model, let's talk about how we write down some of the aspects of atoms. So, first of all, we have something called the proton number. Proton number. Sometimes called the atomic number. Atomic number. But it makes more sense if you call it a proton number. It has a symbol Z. That's a slightly wonky Z there. Let's try there. That's better. And it really tells us the number of protons. Number of protons in the nucleus. It also tells us the number of electrons, E minuses, orbiting. So the number of electrons in a neutral atom. Because the number of electrons must balance the number of protons. Remember that a proton has a +1 charge and an electron has a -1 charge. These are relative charges. So they're the same magnitude, but they're just opposite charges. Okay. Now the proton number defines the element. Defines the element because chemically, the number of electrons and the number of protons tells us how the atom will bond with another atom. And so the chemical nature depends on the proton number. That is what changes the element. If you change the proton number, for some reason you lose a proton, then you'll change the element. For example, we've got helium, which has got 2 protons and 2 neutrons in the center. There we are. Come down a bit now. Excuse my rather dodgy drawing there. And we've got hydrogen, a hydrogen atom, which is the simplest of all atoms. It's just got a single lone proton and 1 electron. In the helium, we've got 2 electrons orbiting 2 protons. So it's a balanced atom. And going on to the other number that's important for us now is called the nucleon number. The nucleon, there's a C there, number. And that's given the symbol A. And that just tells us how many protons plus neutrons. Now this is stuff which you probably already know, but it's always worth going over. And it's sometimes called the mass number. You chemists out there may well just call it the mass number, but us physicists, we call it the nucleon number. So if you were to want to do a little bit of mathematics on this, we would say that A, the nucleon number, is equal to Z, or Z if you're from the States, but to each Z, atomic number plus the number of neutrons. And you could, this is called the neutron number, if you like, but we don't use that very often. Just think of it as the number of neutrons. Okay, so how do we write elements? Well, for example, carbon 12 has 12 protons and neutrons in its nucleus. It has 6 protons. So here is the mass number, the nucleon number, and here is the proton number Z, and you can remember it because it's A to Z going from top to bottom. Oops, I have to get rid of this. Okay, sorry about that. Back to where we were. So yes, we've got the nucleon number at the top. It's a bit kind of strange because it's everything is at the top. You would expect it to fall to the bottom, but it doesn't. It's at the top. And we've got the proton number down here. Six protons in a nucleus of carbon. That must mean it's got 6 protons and 6 neutrons to make up the mass number or the nucleon number of 12. We would usually write this as carbon 12, because carbon is defined by having 6 protons and 6 protons, and the 12 is the mass or the nucleon number. Okay, this brings us on to isotopes. Now, what is an isotope? Isotope. Well, this is an important one. Well, this is all important, but this is particularly important. An isotope is a form of an element which has got the same atomic number but different numbers of neutrons. So it's a form of element. It's got the same Z, same proton number, but it's got different mass number and different nucleon number, wouldn't it? Or different, but we'll just say numbers of neutrons. So in other words, you could have carbon 13. Now that would be C, which has got 6 protons, because that's what defines an atom of carbon. But now we've got 13 things in the nucleus. We've got 6 protons and 7 neutrons. 7 neutrons. And that's the same element, but it's just a different form. It's more massive. Slightly more massive. It will have the same chemical properties, though, because it has the same number of electrons orbiting. If it's a balanced atom, it'll have 6 electrons as well as 6 protons. So chemically, this isotope, this is an isotope of carbon, will have the same chemical properties. And you can even have carbon 14. Carbon 14, and some of these isotopes are actually used in carbon dating. So carbon 14, how many neutrons would an atom of carbon 14 have? Well, it's just 14 minus 6, and it's going to have 8 neutrons. 8 neutrons and 6 protons, because they make up 14. So, just to finish off this section then, 3 isotopes which are quite important when we go on to talk about fusion are hydrogen, so that's hydrogen 1, something called deuterium, so this is hydrogen, deuterium, which is hydrogen, but it's got a 2 mass number or nucleon number, and tritium, which is again hydrogen, 1 proton, but it's got 2 neutrons in its nucleus. So they are all chemically the same, but these guys, let's just draw that down like that, but they will have slightly different masses. This one will be about twice as heavy as this guy, and this one will be about 3 times as heavy as the normal hydrogen. They will still chemically bond with oxygen to form water, and that's where you've probably heard of heavy water. Heavy water is when, for example, deuterium bonds with oxygen to form heavy water, D2O, sometimes called. Okay, we'll stop there for the moment. That has brought us through a big section of constituents of the atom, featuring the electron, featuring the proton. We haven't talked much about the neutron, other than how we write an atom down in terms of its atomic number and its nucleon number. But I hope that's been of some use. I will catch you at the next one.